Hi everybody, so this is the tutorial that goes along with the last of the hand rules, third hand rule, which talks about magnetic force. Okay, the first two rules focus on magnetic field intensity. This is the magnetic force when you have a current carrying wire or moving charges cutting across a magnetic field. Okay, so we learned in class it feels a sideways force when you cut across. We'll talk about the direct, so the hand rule tells us the direction is that sideways, is up, down, left, right, in, or out. And then we'll eventually talk about what the magnitude is, how to calculate that for two different situations. So the first rule as shown in this diagram here is you point the right thumb in the direction of the current. Okay, if it's a moving charges, then you want to do it in the direction of the velocity. So depending on the situation, one or the other. Then you point your directions in the finger of the magnetic field. We'll call that B field. And remember, magnetic fields always point from north to south. Sometimes the magnetic field will just be given by an arrow, and that's pretty easy. Other times it will be given by having some permanent magnets there. Okay, so I'm just going to put N to S just to remind you that. And if you look in this picture, the B field is pointing upward on the paper. The motion of whatever it is pointing to the right. So our palm is pointing up. Out of the page, okay? So I know it looks like, from your perspective, it looks up, but if we're doing from the relative to that page there, it would be out. So the palm points in the direction of the force. And that's called a lorentz force, FYI. You'll hear me use that term every once in a while. That's specific to these magnetic fields. Okay, so let's do some quick practice. We have these X's in a rectangular array, and then we have these four arrows. The four arrows represent segments of wire that form a loop, and the X's represent our magnetic field. Okay, and X means into the page. So if you notice that they're evenly spaced, that tells you that our magnetic field is uniform. We don't know why it's uniform. We could say, well, it's because we're inside a solenoid or whatever. So I want you to write or draw a force arrow for each of the four segments of wire. So pause this right now, work out the third hand rule, make sure you can apply it, and then restart to see if your answers are correct. Okay, so if you did it right, you should have had an upward force here, a rightward force here, a leftward force here, and a downward force, and then a leftward force. I can't really show you what I'm doing, but I can describe it. For this one, I take my right hand. Why my right hand? Because we're assuming this is current going through the wire, and current is always using the right hand. I'm going to point my thumb to the right. The magnetic field is into the page, so I'm going to point my fingers into the page, and when I do that, my palm is pointing upward. And then I do the same thing for each of the other segments, and I get the same thing. So we can then ask, what's the net force? The net force on the wire is going to be 0. So the wire is not going to go anywhere because of those four segments. However, if that wire was elastic, it would expand by that force. So that's an interesting outcome. All right, try example 2. Okay, so if you did it right, you should have had the force going up on the page. How do we get that? Well, I would point my fingers from north to south. So I'd point my fingers to the right. The current is coming out of the page, so I'd point my thumb straight out of at me, and if I do that, okay, I see my palm should be pointing up, and so that wire is going to be forced upwards. And notice that force is sideways to either one. I'm going to put one more example here, and then once I do that, I want you to pause and try it yourself, because again, it's very important. So I'm going to do it in this space here. Let's call this example 3. So let's say I have magnetic fields pointing to the right, so that's B, and I have an electron, let's say, let's put a E negative, moving to the left. What's the direction of the force? So this one proves to be a little bit trickier. If you try to use your fingers for the B field and your left, because it's a negative, thumb for the V, you'll notice that you can't fully extend them. Because remember, when you're using your finger and thumb, they always have to be at right angles, and you can't do that here. So what is that telling us? The force is 0. There is no lorentz force because this charge is not cutting across the B field. It's going anti-parallel to it, and so because of that, there is no force. So be mindful of that when you're applying the third-hand rule. If it's not cutting across, there is no force. All right, so now let's look at the magnitude. So the strength of that force, right? Well, the force arises because you have a current cutting across a magnetic field. So if we want to understand the magnitude of that force, the FB, the Lorentz force, it would make sense to depend on the current. It would make sense it would depend on the magnetic field strength, B and I. From the previous problem we just did, I erased it, sorry, where the electron is moving anti-parallel, we also see that the angle matters. If you're going at a 0 degrees relative to the field, there's no force. If you're at 90 degrees, it's actually maximum force. So there's an angle part. There's actually a fourth component that's the least obvious, and that's the amount of wire that's actually cutting through the magnetic field. So let me just go back to this example up here. If I were to extend this wire out to this length and call that L, the part that's from here to here is not in the magnetic field, so it feels no force. So I want to take the part that's actually in the magnetic field, and that we would label as length. So long story short, our equation for magnetic field intensity, at least as it's written in the reference tables, is I times L. And this is how it's written in the reference tables, okay, cross B. And I'm writing it in the vector form because I want you to understand that this is a cross product. And we're going to translate that cross product in a second, okay? So IL cross B, the cross means we have to have them crossing each other, so the angle matters. So if we want to translate that into magnitudes, I'm going to rearrange the order. That's simply the magnitude of your B field multiplied by the magnitude of the current, multiplied by the length that cuts through it, times the sine of the angle. So it's this form we're going to use most often, but I want you to recognize this from the reference tables. So I call this the Bill equation because usually theta is 90 degrees, and that's where sine of 90 is 1. So the maximum force is when sine is 90 degrees, no force when you give no angle. So we'll do a practice with that in a second. But a little FYI is to talk about B field intensity in units. If I take this equation and rearrange and solve for B, I see that it's equal to force over IL, assuming the angle is 90 degrees. So the units of B are the same as the units of force divided by current times length, or Newton per amp meter. So I believe in the previous tutorial from the first-hand rule, I defined the units of field intensity. They actually come from this equation, and a Newton divided by amp meter is defined as a Tesla. So that's where that comes from, whereas in the previous tutorial I did not derive that. Okay, so in terms of B field intensities, how strong are magnets? If you were to, let's say, look at the Earth's magnetic field, we would find that it's actually fairly weak. Okay, and the Earth's magnetic field is roughly 10 to the negative 4 Tesla. If you compare that to a pretty strong rare earth magnet, rare earth magnets are in the order of 10 to the negative 1 Tesla, maybe approaching 10 to the negative 0 or 1 Tesla. Really strong electromagnets like you find in an MRI machine or in other industrial uses, maybe 3 to 5 Tesla. And then if you get the strongest magnets that you can possibly get, which are used for turning high energy particles, you're only approaching 10 to 20 Tesla. So a Tesla is a very, very, very strong unit of magnetic field, and most of the magnets we encounter are much less than that. Okay, so let's finish up with two problems. So I have a half of a current carrying wire of a certain length cuts across, with a certain current cuts across a B field, and I want to know what is the magnitude and direction. All right, so use the third right-hand rule to calculate or figure out the direction of that field right now. Press pause. Okay, so point your thumb in the right hand to the right, your finger should be pointing down, and you notice your palm is pointing into the page. And in terms of calculating the magnitude, FB, we're just going to use Bill, BIL sine theta, and B is given 0.60 Tesla. It's pretty easy. That should be a Tesla, times 0.50 amps. Now it's the length part that I just want to make sure we're clear of. The length of the wire is 0.75 meters, but only half of it is cutting across the magnetic field. I'm just Xing that out. I don't know what I'm trying to draw there. So it'd really be 0.75 divided by 2, half of it. and then the angle is 90 degrees. So you can plug and chug in there. I'm confident you can get that, and you get 0.11 newtons. All right, let's look at the last situation. So when I showed you the electron tube with the beam of electrons being deflected by the magnetic field, how much was deflected in part was determined by the amount of force. And so what we want to do is, if we remove a wire and we have charges, we want to change the Bill equation to an equation that expresses force as a function not of current, but rather of the amount of charge, and not of length, but rather how fast it's moving. So we're going to change Bill into another equation. It's a pretty simple derivation. Okay, so that's what I'm saying here. We want a magnetic force in terms of charge and velocity, because that's the easiest way to characterize a moving particle, instead of current and length. Magnetic field intensity from something external to the charges is still important. So let's start with Bill. We're going to assume 90 degrees. And the substitution we're going to do there is current, right? What is the definition of current when applied to moving charges? So you might be thinking Ohm's law, voltage divided by resistance. Well, that may be true for the circuit that creates a current. That's not what current is defined as. Current is defined as the rate at which charge moves, delta Q per delta T. So if I substitute it in there, then I've got Bill, or force equals B times delta Q all over T, and excuse me, times L. So I got the Q part in there. Now where's the V come in? Well, I want you to recognize that length divided by time is nothing more than V. So that becomes B, Q, I'm going to get rid of the delta sign there, V. So what you will see in your reference tables, once again, is a slightly different version of this. You'll see that the force, the magnetic force, I'm going to write here what they'll put FM, but I put FB here. Okay, as the product of QV cross B. So the important thing is, like current and magnetic field, the motion has to be perpendicular to the B field for there to be a force. Q is a scalar, so we just put that out to the side. So long story short, we can just combine, assuming the angle is 90 degrees, that's just, well, we don't have to, we'll just say QVB sine of the angle. And usually that just reduces to QVB. And note, if the particle is negative, then we use the left hand for the right hand rules. So the last problem we want to do is fairly straightforward. I have an electron moving to the left. It cuts across a magnetic field that's upward. What's the magnitude and direction of the force? So again, pause, work out the correct hand rule to determine the direction of the force before we solve for the magnitude. In fact, you should really solve for the magnitude as well, and then check back in when you restart. Okay, so in using the rules for the direction of force, it's an electron, you should be using your left hand. So you point your thumb of your left hand to the left, because that's the direction of the velocity of the electron. Your fingers are up, and we should see our palm is pointing out of the page. Whoops. Now, I hope you already solved for the magnitude, okay, because there's two things you got to be careful of when you apply the equation. So the equation's pretty straightforward. That's going to be QVB. It's just an issue of what you put in for Q and V. Q is the electron's charge, and I hope you didn't put in -1. You should be putting in 1.6 times 10 to the negative 19th. And we don't put in a negative because that doesn't affect the magnitude. So that's coulombs. The velocity, okay, maybe you didn't recognize that, but little c is the speed of light, 3 times 10 to the 8th meters per second. That's a convenient way of often expressing the motion of electrons because they're usually going pretty fast. So if I multiply that by 0.1, I should have really 3 times 10 to the 7th meters per second. And then I multiply that by the B field, which is just a generic 0.12 Tesla. Okay, so that's how I calculate it. And when I do calculate it, I should get a value of around 5.8 times 10 to the negative 13 newtons. All right, so the subsequent practices will really put you to test on all sorts of applications. So it's really important you feel good about this foundation before we look at other ways of having current or particles cut across B fields.